Good morning and welcome to this 7th lecture on adaptive signal processing. So, today's lecture we will look at the least mean square filter or algorithm, more popularly known as LMS. So, this is one of the simplest and effective algorithm for which adaptive signal processing is popular. Let us look at more about what this algorithm is, and as you would see that this is kind of a natural extension of what we have seen so far in terms of using a steepest descent like approach to do updates on weight and accordingly adaptation. So, what is this LMS algorithm? So, recall that in our previous module we had looked at a steepest based gradient descent based iteration to update these weights, right. So, if we have a weight at some time which is Wn, we looked at how that can be updated at time n plus 1 by looking at the gradient of the error along with the step size, right. So, we could rewrite by substituting for this gradient. I strongly recommend that you just go look at how this gradient was done in the earlier module. This is something which happens very often in this adaptive filtering setup, where you always have an error function and we are interested in obtaining a gradient, right. So, if you change the error function, the gradient will change and accordingly updates can change, but this is something important to know as a tool. So, do check what is this gradient, and what you would see is that if you do this gradient, we would end up with Wn plus the step size mu times the expectation of E of n times x star of n, right. So, this is something which we have seen earlier, and if I go ahead and assume that this is a Whitesand stationary process, we would end up an update for Wn plus 1 in this form, that is, it is Wn plus step size times this term here, and as we know this term for an Whitesand stationary process will become 0 and this Wn plus 1 will converge to Wn, right. So, this is what we saw in steepest descent, and this is just rewriting it here, rewritten here, right. But here note we have used this expectation and hence we have this cross correlation on the autocorrelation term, but expectation is a statistics which needs to be estimated, right. So, if at all if it is a Whitesand stationary process, this was fine, but if it is not a Whitesand stationary process, or if we do not want to know the statistics of this signal which we are interested in, that means either we need to estimate this expectation term at every instant of time, or somehow find an approximation to this expectation which could be evaluated or computed as we move along in the algorithm, right. So, one possible approach or an estimate for this expectation, as is very common and very popular, we could look at like the sample mean kind of thing, right. So, in this case if you look at the sample mean, what is the sample mean? We just have to agree on certain number of samples to obtain the mean, and if it is so, as in other cases, we will just do sigma over L0 L up to L, E of n minus L and x of n minus L. This assumes that we can estimate the error, and then since our input is x n minus L, we could obtain this estimate, right. So, this seems like a reasonable estimate for the expectation, and one could substitute this expectation with this term, and that will help us get away from using any pre-computed or prior knowledge of the statistics. But there is one minor disadvantage with this approach, that is how good this estimate depends on how large this L is, and so if you make the L larger and larger, we could expect the statistics to be better, but that is again not guaranteed. That depends on the so called stationarity of the signal. If it is a kind of more or less Whitesand stationary or stationary signal, this L would not play a bigger part and we would get a good estimate of the expectation always. But if it happens to be a non-stationary signal where the statistics changes with time kind of significantly, so for example a speech like signal, this choice of L is very critical, right, which means depending on the L we choose, we may have a bad estimate for this expectation. So, how do we get around this problem? So, the idea behind this is very simple. You can just look at any signal you are interested in. If you want to find what is the mean of this signal, one approach is like as we said before, looking at the sample mean. The other more naive and simplest approach is just look at the sample and say that is the sample value or the mean value of that signal, right. So, what is this doing? This is saying essentially instead of using L to be very large, just use L as 1 and say that is my expectation or mean, right. So, this is what we refer as, let us say, a one sample mean. Is this good? It does not seem like it is a very good choice, but what has been found is this is a very effective tool, and this helps us in reducing the computation significantly, that taking just one sample mean is sufficient, right. So, this is kind of the main idea behind this LMS algorithm, and this is why this LMS is so popular, that computationally it is so simple, right, and also effective. So, what we have done, this LMS algorithm, we approximate this expectation by just this E of n, x of n, essentially just drop the expectation and just use as is the signal, right. So, if we do this, then what do we end up? We end up with an update algorithm for the weights as shown here, that is this Wn plus 1 at some time n plus 1 is this Wn plus mu times E of n times x of n, right. So, that seems like a easy thing to do, because it is easy, because E of n is the error we computed at some time, x of n is just the input signal. So, just recall that here x of n is also a vector, right. So, this is a set of input signal coming in, we want to find d of n. How do we find d of n? We know d of n is this d of n, which is assuming that we have a desired signal, times an inner product, which is W transpose times x of n, right. So, in this case it would be Wn, right. So, this if we can compute, then this all the computation is involved in updating this Wn plus 1, right. Of course, the other critical part is this factor mu, right. So, this mu has to be chosen appropriately, as we saw in our discussion on strip persistent. This could lead to convergence or divergence of this weight update, right. So, now we need to look at how this mu can be bounded and how to obtain this bound, right. So, as we see from here, in this case there is no statistics in getting Wn, that is we just have the input signal and the error signal to obtain Wn plus 1, right. So, to understand the convergence, we need to look at a more generic case, which means you need to look at many such realizations, and from these realizations we want to see how these weights behave, right. This is slightly different from the strip persistent approach, because where we just assume that there is statistics estimated. So, which means in this case we need to look at the expectation of these weight updates, right. So, to get this expectation of this weight updates, as you can see it depends on this error. So, let us just look at what is the gradient of this error function. This error function is something which we have seen already. This is what we wrote in the previous slide. This gradient is essentially 2 times the expectation of this term here. So, we in LMS have approximated this gradient to be just drop this expectation and just use this term here, right. So, while that is fine as just the gradient, what we are, like as I mentioned, is we are not just interested in Wn plus 1, we are interested in Wn plus 1 for several realizations of a similar process, right. So, because we are doing for several realizations of a similar process, we could only say something about the average behavior of these weights and not the exact behavior of Wn. That is, given any input signal, if I am running an LMS algorithm, we can't say much about the weights, but what we can say is, if we assume that there are many such realizations and a similar system is being modeled, then we could say something by looking at the expected value of these weights, right. So, we need to look at this expected value of weights and see how these weights converge, right. So, the only thing we need to take over from here is this expected value of this gradient, or the estimate of the gradient is essentially the gradient of this error function. So, if we now look at what is this expectation of these weights, we need to look at how does this weight get updated. This again we will do as we have done in the past. Wn plus 1 at time n plus 1 is this Wn plus the scale factor mu times this difference, which is the error mu. This, as I said, was this E of n right. So, this is what we said E of n is times x of n, right. Here we are not using any note, we do not have any expectation here because this is an LMS which we are trying to update, and then we just rewrite it in a form that we could group all the Wn's together, right. So, if you do it here, so this has to be again Wn and again the Wn here, right. So, what do we want? As I mentioned, we need to look at not just the weight, but we need to look at the expectation of this weight, right. Expectation, because every realization will have a different weight update, right. So, what is this expectation? We just apply this expectation across this in this equation, which is expectation over this weight plus mu expected value of this times mu expected value of this, right. So, here we need a simpler form for this, and if you look at the term here, these are a coupled variables. So, Wn itself is a random variable, as we said, that is why we are looking at this expectation, because it is for every process, and this x is also a random process or a random variable, right. So, we could not just separate them, because we can't say that it is independent, because the weight at the previous time is influenced by the input at the previous time, right. But however, to make this thing simpler and without loss of generality, we will assume that the weights and the input are independent, okay. This may not be entirely correct always, but assuming that this is independent, this helps us move forward. So, if we rewrite this equation, these things come just straightly directly. Only thing here is we need to rewrite this, and we could rewrite this by moving around the expectation as Rx times the expected value of the Wn, right. So, regrouping this weight terms, we can rewrite this as I minus mu Rx times expected value of Wn plus mu Rdx, right. So, this of course, we have brought in this terms of Rx and Rdx. This is only in an analytical sense that we are just representing these expectation values, right. So, this is not in the algorithm itself, this is only for analyzing the weight update behavior of the LMS algorithm. So, this, if you recall, is very similar to what we had in the steepest descent module, where we looked at how the perturbations in weight converge, right. So, we will use a similar notation, and if we say that, then this becomes expectation of this Cn plus 1, which is the weight vector we saw there, or the perturbation in the weight vector we saw there, which is again just rewritten here. So, if we follow the discussion there, where we talked about the evolution of weights in the steepest descent, it is exactly the same discussion, except here we have an expectation, where there it was the actual Cn plus 1. And we could show that this, again after doing that eigen decomposition mappings, we could show that these individual elements of that weight vector again have a similar behavior, and this will converge only if this expected value of Un tends to 0, that is, this Un tends to U0, which means then the difference will be 0, right. So, if you, since we have a very similar and same condition, the condition for convergence of this LMS is again as we saw before, that it is going to be greater than 0 and less than 2 max, okay, 2 by lambda max. So, I strongly encourage that while we are not deriving it here, it is just worth looking at what happened in the steepest descent, so that you convince yourself that this bound on mu is exactly same as what we saw in the steepest descent, and the way we derive it is also exactly same, right. So, the only difference being in the steepest descent, we had an expectation in the weight update directly, whereas in the LMS only for analysis we are looking at the expected value of many such realizations of the weights, okay. So, weight is like a random process here, right. So, with that notion, so we will just look at how or what are the implications of having such a bound on the mu in the LMS case, right. So, while it is nice that we have a bound so that we could choose mu, but then this kind of contradicts what we wanted in the beginning, that is, we said our mu will not depend on any statistics, but we do know that this lambda max is the eigen value or the maximum eigen value of the autocorrelation matrix. So, we need some way of getting around this issue. So, again there what we could do is, so instead of trying to get Rx directly, we need to see is there some other way that though we may not know Rx, we could get lambda max, right. This is one, And also the other kind of subtle thing is, so just say for example this lambda max depending on the matrix may not be a very large value, right, if you normalize further. This may be a small value, and this bound, that is 2 over that small value, can be a large number. So if it is a large number, then the variations for mu can be also very large, right, from 0 to any value which is very large depending on what this 2 by lambda max is, right. So if that is the case, then that also seems like we need slightly better or kind of lower bound this upper bound, so that we get some control over mu, right. So how do we do this in a more data dependent way and not try to do this from statistics? Is we bound this lambda max by this term here, which from linear algebra is kind of well known. This is the lambda max, it's assuming this is the autocorrelation matrix more or less well conditioned. This lambda max is upper bounded by the sigma of all the lambda eigenvalues, which can be thought of, or which is equivalent to the trace of the autocorrelation matrix Rx, right. So this trace of the autocorrelation, see, recall this Rx as some R0 at this diagonal. So if you look at this trace of this Rx, you can show that for this positive definite matrix, this trace is essentially Rx0 times the p plus 1, because all the diagonal values will be equal. Again, this is not an estimated value, we are just thinking analytically this is true. And what is Rx0? It is essentially power in that signal, which can be just thought of as shown here. This is the expectation of the x of n whole square, right. Of course, this one again we are having an expectation, but as in the earlier case, we would try to estimate this thing from the given data. So how do we estimate that from the given data? It is again sum of over n samples of this given input data. So if we could do this, then rather than choosing a mu and bounding it with some value, we could get a realization of this process, obtain this term here, which is again an average over some n samples, use that here, and then that will give you a bound on mu, right. Well, this seems a bit restrictive that we need to know the signal. In practice, this is not very bad, because you just need some initial set of samples to obtain this value, and once you get this value, you can bound the mu. Once you know, or once you choose a mu which is within the bound, you could vary around that bound to get better convergence. You can again recall to the discussion we had in the steepest descent, because this mu also indirectly kind of controls the rate of convergence, or the rate or time it takes for the error to converge to some small value, right. So the choice of mu is really critical in also the LMS algorithm. If you make mu greater than this lambda by 2 max, this algorithm will not converge and you will have results which you do not expect to have, right. So it is critical that you choose this mu in a more careful and appropriate way, rather than just taking things randomly. This is especially true if you want to realize a system which is going to use this LMS update, right. So we will just check if even if we choose this mu to be some bounded value, what happens to the minimum error, right. So we know in the Whiteside stationary case, the minimum error has to be that zeta error which is minimum, but do we reach that zeta minimum, right. So that is something which we want to answer, and to answer this we need to just understand that the LMS, the underlying approach is steepest descent, which is the gradient update, and when you are estimating this gradient, at least in the steepest descent, the way we discussed, if you have statistics or access to statistics, these gradients were kind of well behaved, whereas now in the LMS, these gradients essentially are just depending on this E of n and x of n, right. So that is going to control how we update the weight, and in some sense this is kind of a noisy update to the weight, right. So that means we need to see what is this update doing to our minimum error value, right. So how do we do it? So let us say for example, we look at this error function which is E of n. We know this E of n is d of n minus the updated weight Wn times the input signal n, right. So what we say is this Wn, even if it is, let us say, the Whiteside stationary case, we are not going to get the exact W optimal in the LMS filter case. In the steepest descent case, you will get exactly the W optimal because it is just R inverse R dx. Here it is not such, because it is an estimate of r and x and r dx we have, right. So, with that constraint we could approximate this Wn and rewrite it as if that it is W optimal, which is what we expect it to, but there is always some small change or perturbation from this W optimal, right. So, this perturbation is kind of similar to what we discussed in terms of how the weights get perturbed in as we go along the LMS updates, but notionally this is how we are indicating it. So, if we do and expand it, what you will have is you have this the minimum error, which is essentially let us say this d of n minus, if at all you have this W optimal, then that is your minimum error, right. But what we have in addition to this minimum error is a error term which is coming from the perturbation of these weights. This perturbation of these weights we are expecting it, this if mu is chosen properly, this LMS will converge. So, assuming that this convergence is true, this term will just be the zeta min term, and this term which is the second term here will lead to some additional error, right. So, there is this excess error or additional error, which as you can see depends on this perturbation, weight perturbation, and depending on the mode which you choose, it will vary differently. That you will reach zeta min, but you will be slightly deviating from the zeta min by a factor which is zeta x, and if you use appropriate simplifications, you could have an analytical value for excess error if you know some statistics. This is only for verification. In practice, we will not be able to get what this excess error is unless we know what the minimum error is, right. So, what does this say? That this just says that in the steepest descent algorithm, when we go use known statistics such as Rx and Rdx, for the Whitestone stationary case we will converge exactly to the W optimal, whereas in the LMS case, even if we use a Whitestone stationary process, we will converge very close to W optimal, may not be exactly stuck at W optimal, it will be deviating or slightly moving around this W optimal, and this movement about W optimal leads to some small excess error, right. So, we should always try to make sure that this excess error also is small, not just minimum error is minimum, right. So, this is again one important behavior which could be seen more effectively in simulations of this LMS algorithm. As I mentioned earlier, so I will probably provide some Python simulations which show how the LMS behaves with respect to changes in mu, the choice of the initial value, and then how it converges either slowly or fastly depending on your choice of mu, right. So, this again it is always good to relate to your that error surface which I had shown in the beginning, because that again will give you some intuition as to your choice of mu and how it controls the error behavior. So, while that is good about LMS, of course, we need to look at an example to understand a little bit more about LMS and see how it behaves. What we also want to kind of at this point look at is, we said that to choose mu, we need a bound, and that bound was lambda max, and if it is going to be bounded by some 1 over lambda max or 2 over lambda max, we need an estimate for lambda max, right. So, it seems that this is kind of a situation which means we need to know some kind of statistics, right. But if at all we choose, let us say that we choose mu appropriately. So, we had this Wn plus 1 is this weight Wn plus mu x of n E of n, right. So, E of n here is a scalar, x of n is kind of a input signal, right. So, of course, in a real world scenario, x of n is just a signal which is coming input to us, right. So, what could happen is, even if we choose mu well below the upper bound, it could possible that there could be a suddenly large value in x of n, such that this whole term can get perturbed a lot, that you will not be able to come back in the iteration or the convergence of this algorithm, right. So, essentially what I am saying is, if there is a sudden change in x of n, like an impulsive change which is very high value, it is possible that your algorithm can go out of convergence region and you will not be able to converge, right. So, it seems that we need a way of handling this situation, that is sudden changes in x of n can affect the LMS convergence, and this kind of leads to us other variants of LMS and properly well known variant of LMS, which again done many signal processing application. If your algorithm depends on the input, it is always safe to use a normalized input rather than trying to use the input as such, right. So, with the same idea we will look at one variant of LMS which is called as this normalized LMS, right. So, this normalized LMS, I mean this normalization is normalization of the input. So, this also, while it helps us handle the situation which I said, another way to look at it is this is going to help us, if you think of the weight updates to have some error, this is going to minimize this errors in during the weight update, right. How does this do? How does this normalized LMS do this? So, recall we have this condition on LMS which is mu should be less than 2 by lambda max. So, again we saw that instead of using lambda max directly, we can have an estimate which depends on the signal energy, which is this p plus 1 times E of x n squared. So, one way of rewriting this is just rather than using this p plus 1, if you substitute this term here, p plus 1 cancels with this p plus 1, this sigma term is essentially x transpose x times x of n, right. So, you see this here what have we done, that this seems like the mu is bounded by this term, right. So, instead of saying that the mu is bounded by this term, we will just make mu a time varying mu, right. So, instead of having a fixed mu which is always some value which depended on a choice we made, we let mu change with the input signal, right. So, now we have a slightly more intelligent step size which is essentially a time varying step size, and how does it vary? It depends on the choice of beta which we have to make, just some upper bound on this is 2. So, there is nothing too much to decide about this, but it is controlled every time by the input signal. So, if at all this input signal has perturbations, then this normalization will help us handle this because our mu is updated. So, if you look at this, you will have using this mu, we have this Wn plus 1 is Wn plus mu n, right, this notionally. So, there is this x of n times this E of n, right. So, you can see this mu n essentially is beta by x transpose n times x n, right, E n x n, right. So, this x n, though even if it has perturbations, the similar perturbations happen in this denominator term here. So, this can be thought of as looking at the signal and normalizing the signal based on the signal energy. So, once we normalize this signal on the signal energy, we will not have such sudden changes in the term here or in the term here, and this helps us the LMS to behave slightly more controlled, right, even if we choose mu to begin with some beta value. A slightly better update is, rather than just letting the denominator control the entire thing, you as in many signal processing application, you add a small or a delta or epsilon value such that even in case if this becomes very small, this whole term should not go to some very large value, right. So, instead you add another epsilon value which kind of helps you make this update to mu behave in a stable way, right. So, this if we ensure that behaves well, this will ensure that our weight update in the LMS also behaves well, right. So, this kind of variants of LMS are quite popular. So, one variant is what I have discussed here. So, there are many more variants which depending on the implementation, we could approximate either x, either E or mu, and accordingly update these weights, which have a very similar behavior as shown here. That is, it will usually not involve many computations. It will usually be made sure that there is convergence, at least building from the original LMS convergence, and more importantly that will always be ensured that computationally this is a very simple algorithm, right. So, that is the strength of the LMS algorithm, that it is very simple, as we saw, it is just a dot product at most, right, because we want E of n, and E of n involves d of n Wn times x of n, and then that multiplied with individual elements of x of n, right. So, as an algorithm to implement, LMS is so simple that you just write this with 2 or 3 lines of code, but the choice of mu is very critical, that the behavior of this entire algorithm depends on what this mu is, right. So, I think what remains to be done with LMS is we need to look at an kind of a simulation of this LMS, because that is one useful aspect of any of this algorithm which we are looking at in this adaptive signal processing course. So, I strongly recommend that you should practice simulations and try realizing some simple systems either in Python or in MATLAB. So, we will give additional material where you could look at such simulations. So, with this I would like to end this lecture on LMS. So, essentially what we have given is what is this LMS algorithm, and then how it helps us in the adaptation process. So, if we have a setup for an adaptive algorithm, you could usually implement it using an LMS, and this is one of the very simplest computationally demanding algorithm, that it does not take much time and many times can also be done in real time, right. So, some of the popular applications of using LMS include headphones noise cancellation, echo cancellation in rooms, and many other things, but all of this just do depend on the choice of mu and the length of the filter you are using, right. So, with that I end this session on LMS. Like as I mentioned, we will provide additional material where you could look at simulations of LMS, and feel free to contact me in case if there are any doubts with respect to this LMS algorithm. So, for want of time we are not going to look at other variants of LMS, these are all in the book on Hayes. Some are important from a practical point of view, some are more important from what if I change the error function. If the error function is mean square error, this is standard LMS. If I do not use the mean square error, and if I use some kind of regularized error function, what will that error function lead to, right. So, these are concepts which are useful to understand, not necessarily from an LMS point of view, but in a more adaptive algorithm point of view. So, thanks for listening, and the next lecture we will move on to look at the recursive least square filter. Okay.